Hello calculus students, isn't technology wonderful where I can be out of the building and you can still listen to me talk to you about calculus? Woohoo! If you haven't already, please make sure to get the warm out handout from the substitute. Note that homework 2 is tonight from your list. It's in the book, and it is actually the first section of chapter 3, because remember we started chapter 3, we think chapter 3 should have started with 2.4 in your book, and that was the first book homework assignment, and this assignment is from 3.1. So this warm-up asked you to draw a parabola. You're probably not going to get any calculus points on an assessment for drawing these things, but I want you to get used to it. Even if you draw it just a rough sketch, it is important that you do know that this parabola has a minimum at 0, -6. It crosses the x-axis somewhere around exactly at root 6 and negative root 6. So that's kind of sort of around here. I note that they want me to draw the point of the tangent line at x equals 3. So I'm going to say, well, if x equals 3, what is the function at 3? And 9 minus 6 is usually 3. So the point of tangency is 3, 3. That's an important point. So I'm just going to, and this with my drawing tool here, forgive how rough my sketch is. So they're asking me to draw the tangent line, so I sketch the graph of f. I need to now draw the tangent line at the point of tangency. And remember that the whole idea of a tangent line is that the tangent line and the curve are exactly equal at one place. The tangent line is up close and personal to the curve, exactly equal to the curve at 3, 3. Because this graph is concave up, my tangent line brushes by underneath, but are exactly equal at 3, 3. And then in this little cloud, okay, not the eye cloud, this little cloud around where x equals 3, right? If you go a little bit to the left and a little bit to the right, those delta x's, which in calculus we call h, correspond to heights or function values on the blue line that are very, very close to the red curve. Now with a curve of x squared minus 6, I don't need to actually approximate values. We're just learning a concept here. Tangent lines can approximate messy curves, as long as you're close to the point of tangency. You can't imagine the calisthenics that so many engineering and computer science systems and programs go through to linearize weird functions, so that because even machines calculate linear values faster than they do nonlinear values. It's called foreshadowing. Okay, so I've done these two things. Now they want me to, oh, dreaded words, definition of derivative is an L word, right? To calculate the exact value of the slope of the curve, which is the slope of the tangent line, at one point. So since it's at one point, I'm going to use the x minus a, since I don't have to come up with a derivative rule or a slope generator. At x equals 3, this is my a value. So the limit as x approaches a, which for me is 3, of f of x minus f of a, but I already found a, right? This is a comma f of a all over x minus a. Simplify, because obviously I can't plug in 3 because I would get 0 over 0. Factor shocker, my bad x goes away, take my a, right, this is the limit as x approaches a, so when I've done canceling out, I can't put a here, can't put a here, can't put a here, but I can now put a here. And I get 3 plus 3, which is 6. I don't have any units, so I don't have to put any units on this, but I do know that a slope is the change in y over the change in x. And it makes sense that this is positive, right? So I think to myself, 6 is positive, and then I look up at this blue line, and I go, yay! That tangent line I drew should have had a positive slope, and bigger than 1. It definitely looks like the slope is bigger than 1. Remember, I could have asked you to estimate the value of the blue line, the slope of the the slope of the blue tangent line by doing rise over run, since I gave you a scale, but I asked you for the exact. But one of the reasons to do estimation, even if somebody doesn't ask you, is to check your work. This all makes sense, that I did the exact value using a limit. I got a value of 6. I looked back at the graph and I saw that the slope should have been a positive number and looks like it should be higher than 1. So now in part D, oh wait, it asked me to write my final answer using the derivative notation. So what I'm going to say is, since this function is f, that f prime at 3 is 6. F prime at 3 is 6. Or, alternatively, I could write the derivative with respect to the independent variable x of the function f, and this is kind of funny notation. It's this little like line. That means at x equals 3 is 6. Okay. This, I have to say, is more common. But please do know that you should be able to read this notation. So use your result from part C, which is a slope, to write the equation of a tangent line. Equation of a line, algebra 1, y minus blank equals blank, parentheses, x minus blank. The slope is always the multiplier on the independent variable when y is by itself, or at least all the x's are over here. So I'm going to take my slope and put it there. I'm going to take the point of tangency, right, point of tangency, because that's where the line is equal to the curve, and put the x value here and the y value here. Again, these are integers, so if you want to get it in mx plus b, fine. I choose to do this. Okay, there's the equation of a tangent line. Yes, that is 6x minus 18 plus 3, which is 6x minus 15. Application of the derivative. Use the tangent line to approximate f of 3.1. Now, I don't actually have to approximate f of 3.1. I could plug 3.1 into here, right? 3.1 squared minus 6. Use my calculator and I'll get an answer. Let's see. I know you can't see me, but I'm using my calculator. 3.1 squared minus 6 is 3.61. This is a point on the red curve on f of x. Use the tangent line to approximate f of 3.1 means that I'm going to go to my tangent line and plug in 3.1. So 6 times 3.1 minus 3 plus 3. Notice that 3.1 minus 3 is a small delta x, right? That's 0.1. and 6 times 0.1 0.6 plus 3 3.6. Wow! Did it do a good job? Is 3.6, the value from the tangent line, a good approximator of the actual function value? Yes. Alright. Moving on. Let's do another definition of derivative, and I wanted to use, instead of, notice in the warm-up I said use the definition of derivative. I want to make sure that you know that when we say use a difference quotient, that is that vocabulary you're responsible for, and you need to know that that means use the formal limit definition. Now I know I say use either form here, but I want you to notice the language. Given 1 over t, and I purposely changed variables on you, to find g prime of t, that's not really giving you a choice in the form, because this says when I ask for g prime of t, this is saying I want the slope generator for all t on this function. Now I do note to myself that t cannot equal 0 on the original function. Here's the graph, right? You can see that there's a vertical asymptote. The graph doesn't exist at 0. Therefore, no derivative can exist at 0. So I do need to kind of use my formal as h approaches 0 of f of x plus h minus f of x all over h. So if you want to pause the video and do this on your own and then see if you match mine. Okay, I'm going to do my work. So 1 over x plus h, or t plus h, minus 1 over x, in this case t, all divided by h. So again, I have to get a common denominator. My common denominator is t plus h times t, which means I'm going to have t minus t plus h all over t plus h times t, all divided by h, but remember I prefer to write that as times 1 over h. So that's going to be t minus t minus h, which is just negative h, over t plus h times t. And shocker, I do get a canceling out. Once I have something cancel out, I'm going to re-plug in negative 1 over t plus 0, right? I'm going to put a 0 in here. And I'm going to get 1 over t times t. T plus 0 is just t, and then t, right? That's not multiplying by 0. T plus 0 is t times t is t squared. This is g prime of t at any x. T. Now I want you to think for a minute. Look at the numerator of my slope generator. Isn't it always negative? if the slope generator is always negative and the denominator is squared, what does that say about the slopes on g of t? Firstly, do you agree that the derivative generator tells you that the slope doesn't exist at 0? True? Now, look at this expression and read it. Negative numerator over positive always because of the squared denominator means that every slope on g is negative. Do you believe it? Are you buying what I'm selling? Take your handy dandy tangent line maker and lay it here. If you draw a tangent line here, isn't that slope negative? Close to 0, but negative. What about here? 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 Right? All of these slopes, don't you agree, are negative. And these slopes here, aren't they, once you jump over the vertical asymptote? This slope is steep, but it's negative. Steep, negative. Getting slower, getting lower, getting closer to 0, getting closer to 0, getting closer to 0, but still negative. Right? Check. Here's another thought. Let's think some more. What is true about a ratio whose numerator is always 1 and whose denominator gets bigger and bigger? Doesn't the value of the slopes approach 0 as x as x gets close, as x gets closer and closer to positive infinity or negative infinity? What? The horizontal asymptotic behavior of a slope generator talks to me about the value of the slopes on g of x. Oh my God, my head is spinning, right? Take a breath. Let's examine derivative behavior with something even simpler. So, we had the warm-up x squared minus 6, and we found that the derivative, the slope, at 3, the point of tangency, was 6, right? The slope on f at 3 was 6. Now, I did not use the definition of derivative to find the derivative rule. But let's suppose I did, right? If I had made you do the definition of derivative, you would have found it, you would have simplified and found that f prime, the derivative, the slope at any x in the domain of x squared minus 6, which by the by has a domain of all real numbers, right? The slope at any x on x squared minus 6 is 2 times the x coordinate. Notice the y coordinate doesn't matter. Just 2 times the x coordinate. So, if I hadn't used the x minus a formula on the warm-up, and if we had gotten 2x, is it true that the derivative then at 3 we could have gotten from this formula? Yes. Alright, so now let's look at this derivative rule, the 2x. And I want you to time travel back to Algebra 1. When you first started plotting points, given a rule, given a function, plotting points, looking how it runs on a graph and saying, this is a pattern. Right? So, Notice that instead of saying x and y, I now have x and slope values on f. M for slope, right? On slope values on f. Slopes is my output. Input, domain. Output is a range, but this range is slopes on x squared minus 6. So when x is negative 1, the derivative is negative 2. Does that make sense? Right? Remember we had, does it make sense? Now we drew the tangent line at 3, 3, right? And we got a tangent line whose slope was 6. Does it make sense that at negative 1, a slope would be negative? Does it make sense that at 0, the vertex, the slope of the tangent line there would be 0? A horizontal tangent line. Does it make sense that at 1 the slope is positive, at 2 the slope is positive, and 3 the slope is positive? Of course here, this was the point that I gave you from the warm-up. Now, if I ask you not what the graph of f, but what does the graph of f prime look like? Again, time travel back to Algebra 1, you're just plugging and chugging, right? But I don't think you're going to be surprised that I am now plotting x's versus not y values really, but f prime of x values. When x is negative 1, f prime of x is negative 2. When x is 0, f prime is 0, and so on and so forth. But read this differently. When x is negative 1, the slope on x squared minus x is negative 2. When x is 0, the slope on the parabola is 0. When x is 1, the slope on that parabola is 2. But hey, those lines form a pattern. I think I'll connect them just like I did. OMG. The graph of f prime is 2x. Well, duh. Didn't you know what that graph looked like? And don't you know some pretty funny things about, some pretty cool things about 2x? Hello, Algebra 1 students. How many x-intercepts does 2x have? Where is 2x positive and where is 2x negative? What are the characteristics of 2x? It's a linear function. It itself has a constant slope. Curious. And it increases over its domain because its slope is positive. Right? Just saying. Okay, you got to keep all of this stuff kind of straight in your head. I'm not doing a whole lot of fancy math here, but I'm doing some pretty fancy interpretation of what this math means relative to my problem. So, when I look at this parabola and I ask you not at a specific x, but can you tell me when the slope would be positive? At what x values are the slopes positive? Negative. 0. Hello? I can answer that for you. The characteristics of 2x answer these questions about x squared, the slopes on f of x. The characteristics of the slope generator. Answer questions about slopes on f of x. So, because you know 2x has a domain of all real numbers, because you know 2x has an x and one x-intercept, and its x-intercept is at 0. Because you know before that 2x increases over its domain and is negative, therefore negative, before x equals 0 and positive after x equals 0, you can answer these questions. Before the x-intercept, this is the x-intercept of 2x. To the left of the x-intercept, any x to the left, I have negative values, but the values on f prime are the slopes on f. F prime is negative, therefore the slopes on f are negative. And again, that should make sense. This is f, all the slopes, right? This is x equals 0. To the left of 0, slopes are negative. To the right of 0, slopes are positive. The x-intercept of 2x is a minimum on f. To the right of the x-intercept on f prime, f has positive slopes. F prime greater than 0, f prime less than 0 talks to me about the slopes on x squared minus 6. So here again is the picture of f prime. Here is the picture of x squared minus 6. I want you to look at some of the corresponding behaviors. Where f prime has an x-intercept, f has a horizontal tangent. Where f prime is negative, f has negative tangent lines. Where f prime is positive, f has positive slopes. Tangent lines with positive slopes. Crazy, right? Where f prime is negative, f has tangent lines that decrease. Where f prime is positive, has tangent lines that are negative. Where f prime is positive, F has tangent lines that are positive. Where F prime is 0, F will have a horizontal tangent. So this is how AP is going to test you on this. Connecting the graph of F to F prime without an equation. So I led you through the warm-up and the 1/t example, and then hitting the warm-up back where you would see the equations of both F prime and F. And I want to see now, without any equations, can you do a similar analysis? So graph the derivative given F. The original. So it bothers me that it doesn't have arrows. So this is the original graph. So use your handy dandy tangent line maker and say to yourself, if I drew a tangent line here, the slope is positive. If I drew a tangent line here, the slope is positive, but as I travel from left to right through the domain, the slope is positive but decreasing, right? As I draw a tangent line here, slope is positive but approaching a horizontal tangent line. As I draw a tangent line here, the slope is positive, and if I draw a tangent line here, the slope is positive, but I said decreasing, but increasing. Can you draw it? So I'm going to again over here say to myself, from negative infinity to 0, slopes were positive and decreasing. At 0, slope 0. From 0 to infinity, the slopes were positive and increasing. And get used to writing things like this, or at least seeing things. Slopes were positive, f prime of x was greater than 0. F prime of x was equal to 0. F prime of x was less than 0. And start to draw that approximately. Over here, my slope was positive and high. So over here, positive and high. Then my slopes, as I started to go through the left of the domain, left to right, the slopes were decreasing. So decreasing, slopes decreasing, 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 until at 0, the slope was 0. Once I passed 0, the slopes were still positive, but they were increasing. So the slope stayed positive, but started to go back up. And at about this spot, this slope value was about the same as that slope value. So I have some symmetry here. Curious. That looks kind of familiar. Now, let me see if you can go backwards. And this is a dagger on an assessment for a kid. If a kid is not paying attention and they look at f and graph f prime, great, and then they go to the next problem and they do the same thing. But here, notice that you are given f. In this one, you are given f prime. I am looking not at the original, at graph of slopes. So when I read this, I don't say the same things to myself that I said when I was reading the original. So going from original to slopes versus going from slopes backwards to the original. Read original, graph slopes. Read slopes, graph original. So I have to change my thinking. So I have to say to myself here, self, as you go through this domain, the slopes are constant. And the slope is constantly what? What value? -1. And then here, what is true? This is an open circle. What does this mean? An open circle here and an open circle here? The slope does not exist at x equals 0. What? What does that mean? Think. Think. Slope does not exist. Does that mean that I have a break in my graph? Wait. Derivative not existing does not mean the graph doesn't exist. It means the slopes from the, not necessarily, it means the slopes from the left are not the same as the slopes from the right. Do you see that in this graph? I hope so. Because over here, when I say to myself, the slopes are also constant over here, slopes are constant, but what are they constantly? They are constantly what? +1. What graph do you know whose slopes are constantly -1? Not the function value is constant, the slope is constantly -1. And then at x, right, at 0, where x is equal to 0, the slope immediately changes to +1. Can you graph that? So, starting here at the left of the domain, go to the graph of f to the left of the domain. Can you plot a slope of -1? I think you can. And -1. As x goes through the domain, the slope is constantly -1 until you hit x equals 0. Then at x equals 0, immediately, what does the slope jump to? 1 and 1. That's the absolute value of x. The derivative of the slopes of absolute value of x. Remember, this is a piecewise function. That is x as long as x is greater than or equal to 0, and the opposite of x, as long as x is less than 0. the derivative exists everywhere in the domain except at x equals 0. The slopes here are -1. The slopes here are +1. The graph exists at 0, but the slope of 0 does not exist. And that's what this graph says. Slopes to the left are -1. Slopes to the right are constantly +1. Slope at 0 does not exist. Calculus is really cool. Yay! Alright. Well, I hope that you enjoyed listening to me while I wasn't there. And try that homework. Remember, I put up on our classroom site, I put the solutions to the classwork handout that we did with the tangents and the tables, the estimating or whatever. I did not put the answers to the packet. So I would certainly expect to see that you have all the right answers on the first single sheet of the handout I gave you on Wednesday. And then I will check the packet on Monday and check this bookwork on Monday. Have a swell weekend.